Hello, I am a PhD student at University of Tehran, Electrical and Computer Engineering Department. I am currently working on energy efficiency of deep neural networks, especially for deployment on devices with energy limitations. For example, battery-powered smartphones or even IoT vision sensor nodes powered by an energy harvester. Here, I'm going to talk about a new way to improve energy efficiency of CNNs. I'd like to discuss three things. First, why we need to deploy CNNs on such energy constrained devices. Second, what is the potential source of the high energy demands of CNNs? Which the answer here is their high computational complexity. And finally, how to mitigate the high computational requirements of CNNs. Today, we see the wide use of machine learning in various pattern recognition and data mining applications. CNNs are considered as an instance of machine learning. Over the last decade, CNNs have rapidly grown in popularity compared to the other ML instances. This is because of the exceptional accuracy levels they offer in these applications. Even in some cases, they have surpassed human accuracy. However, this high degree of accuracy involves high computational requirements. These high computational demands of CNNs translate into energy inefficiencies, which make us unable to deploy CNNs on devices with energy constraints. So here it comes the question, how we can meet the high computational demands of CNNs in our applications. One solution is to offload the processing to powerful resource-rich servers called the cloud. This leads us to a computing paradigm called cloud computing. In cloud computing, the cloud servers are located far from the end devices. So, the communication between the cloud and the devices is through a long-distance communication network, for example, a WAN. Although cloud computing satisfies the high computational requirements of CNNs, the long-distance communication network causes several issues, making cloud computing not a viable solution on its own. Here, I'm going to talk about three of them. First, offloading the data processing to the cloud may threat the real-time requirements of time-sensitive applications such as robotics, self-driving car, and augmented reality. This is because of the delay associated with the distance network. Second, computation offloading may involve sensitive data such as camera images, GPS coordinates, and microphone audios, which raises privacy concerns. Finally, connectivity between the cloud and end devices is not always possible. Also, in some cases, the connectivity is transient, for example, oil fields. All these problems show the importance of performing the data processing in a very close proximity to the device. This introduces a new computing paradigm called edge computing. With edge computing, we try to perform the data processing near the device, and the device is usually constrained in terms of energy. So, this leaves us again with the original problem, high computational demands of CNNs. To solve this problem, we should look for its source, that is, the internal structure of CNNs. A CNN is composed of several convolutional layers. Convolutional layers are responsible for extracting higher-level abstractions of the input data, which we call them feature maps. In fact, the high accuracy in CNNs comes from these high-level feature maps. In Figure 2, you see a convolutional layer composed of arrays of input feature map, output feature map, and kernels. We can summarize the main computation within a convolutional layer in a sequence of MAC operations. Equation 1 shows the computation for a single activation called xout. In CNNs with several to tens of convolutional layers, this number is surprisingly significant, something about 600 million for AlexNet and 15 billion for VGG16. Table 1 shows this. These numbers are just for one single image classification task. So, the huge amount of MAC operations in convolutional layers is the cause for high computational complexity and thus the cause for energy inefficiencies in CNNs. Let's see how to cope with the huge amount of MAC operations. Many studies have focused on MAC reductions employing prediction techniques. This is comparable to the conventional prediction techniques in the context of computer architecture, for example, branch prediction techniques. With this approach, we identify and skip the computations with tolerable or no effect on the application's final output. In convolutional layers, these computations are those resulting in zero activations. On the other hand, empirical observations show that a huge number of output activations in a convolutional layer are zero. In fact, on average, near 50% of total pixels result in zeros for most of the CNNs. So, zero prediction or sign prediction has been the focus of many studies. Although there is a variety of works trying to identify the activations that can be simplified to zero, no one has considered examining the possibility of other simplifications. In our work, we tried to simplify a MAC-intensive convolution operation into a less complex computation. We called the convolutions with this property reducible convolutions. Okay, now it's time to talk about our contribution more precisely. First, what is a reducible convolution? Let me clarify it with an example. This is a very simplified version of the computation within a convolutional layer. It shows the required computation to calculate the partial value of a single output activation relating to just a single channel. The computation here is a weighted sum of input activations. If we factorize this equation based on the weight parameter, then the equation approximately reduces to this. Here, W is the result of applying an aggregation function to the weights. In a similar way, we can factorize based on the input parameter. Okay, we can extend these simplifications to the general form shown here. F and G are aggregation functions applied to the kernel and input arrays respectively. This equation implies that with this factorization, we can reduce a convolution with k-squared MAC operations into product of two inexpensive aggregation functions. When we simplify a convolution operation, the difference between the simplified value and the actual value may cause error. Some error values do not affect the final output's quality. This is because of the built-in resiliency existing in most of the computer vision applications. However, some error values may affect the final output, which is not desired. So, when applying a simplification, we must make sure it causes no error or it causes a degree of error tolerable by the application. In our work, we control this with a threshold called simplification threshold. The general definition of a reducible convolution is shown here. A convolution operation is reducible if both these equations hold. The second equation refers to the fact that computational overhead concerns only arise with the input aggregation function. This is because we can apply the kernel aggregation function before the inference phase since we have the kernel weights. However, we have storage overhead associated with the kernel aggregation function. This is because in addition to the kernel weights, the aggregated weights must be stored for use in the inference phase. For the input aggregation function, we used max and average pooling operations because these are the most widely used pooling operations. However, other pooling operations can be used. The computational overhead of these pooling operations are much less than a convolution operation. This is because a pooling operation is a sequence of add operations and an add operation is computationally much more inexpensive compared to a multiply operation. Factorizing based on the input parameter using max or average aggregation functions leads to the sum aggregation for the weight parameter. So, with all these considerations, we defined three types of reducible convolutions. A convolution is max reducible if f is a max function and it is average reducible if f is an average function. In addition to max and average reducible convolutions, we defined zero reducible convolutions as the convolutions that can be zeroed. Here we see our proposed convolution factorization approach from the architectural perspective. As shown, a standard convolution operation of kernel size R by S is reduced into a max or average pooling operation followed by a convolution of kernel size 1 by 1. In the next slide, I am going to discuss how we identified reducible convolutions in a CNN. Assume that we have a CNN, let's say AlexNet, and we want to improve its energy efficiency by reducing its MAC operations. To identify reducible convolutions and determine the type of each convolution, we proposed a multi-class predictor. We called it Reducible since it takes its basic structure from a binary predictor called ZAP. The Reducible predictors are incorporated into the desired layers. This figure illustrates the prediction approach in each layer. It's a three-step approach. First, a subset of activations are initially calculated using the standard convolution operation. This generates the partially computed off-map X outside S. This subset of activations are determined by dark pixels in a predefined mask. The white pixels determine the set of activations to which our prediction approach will be applied. Next, we fit this partially computed mask into the predictor as an input, and the predictor generates a mask for the remaining activations. The mask values are integer values between 0 and 3, which determine the type of each activation. Finally, based on an activation's type, an appropriate processing is applied. Zero reducible activations are skipped, max and average reducible activations are factorized into max and average pooling operations, and irreducible activations are computed using a standard convolution. Okay, let's get into know our Reducible predictor more precisely. Similar to ZAP, we use two convolutional layers. In these layers, 2D kernels are used by eliminating the channel dimension. This elimination reduces the number of MAC operations and the weights because the number of channels in a convolutional layer is a very large number, more than 100. Within the generated feature map from the last convolutional layer, each activation is a real value with integer and decimal parts. The integer part determines the simplification technique that if applied to the activation, it gives the minimum difference relative to the actual activation's value. The decimal part, on the other hand, gives the difference value, which is normalized in the range of 0, 1. We trained our predictor in a way that gives us such information. If a predicted value exceeds the range, we clamp it. Next, the simplification threshold is applied to the differences matrix. Here, if a normalized difference value is below the threshold, it means the error caused by simplifying that activation is tolerable. Okay, for the activations with the simplification types class predicted as 1 up to 3 in the simplification types matrix, these activations are identified as reducible, with the predicted class determining the type of simplification. Otherwise, they are irreducible. Here we have the final output. Now, let's see how much max saving is offered by our proposed approach, and also see this max saving comes at the expense of incurring how much storage overhead. This equation shows the max savings. It depends on both the size and the number of kernels. This is comparable to the amount of max saving offered by the existing embedded deep neural networks such as MobileNet. Here, the scaling parameter exists because of using a pooling operation. However, this number is not realistic since the equation only holds when all the activations are max and average reducible. For zero reducible activations, max saving is a larger number, and for irreducible activations, this number is smaller. So, we will see the actual max saving in our experiments. This equation shows the storage overhead, which highly depends on the size of filter as well as the number of simplification techniques. This means the storage overhead limits the number of simplification techniques that can be used. We calculated the storage overhead of our proposed prediction approach to be increased by at most 2%. This covers our contribution. Now I'm going to talk about our experimental results. For our experiments, we use a pre-trained version of AlexNet as the host CNN, and we use the configuration shown here to train our predictors. AlexNet has 5 convolutional layers, and we incorporated our trained predictors into all the layers except the first one. We conducted 2 series of experiments. The first one showed the potential max saving benefits using reducible convolutions inherent in convolutional layers. The second one evaluated our proposed prediction approach and showed how much of these potential max saving benefits have been exploited using our predictors. Let's see the results of the first experiment. Here we see shares of each reducible convolution type in an off-map for each simplification threshold. And here the shares are reported for each convolutional layer. I'd like to discuss about 4 observations. First, the convolution reductions increased with the threshold's value. Second, on average, near 53% of MAC reductions were provided by reducible convolutions, from which near 10% pertain to max and average reducible convolutions. This shows the potential extra max savings that can be achieved using other simplification techniques than zeroing a convolution. Third, the number of average reducible activations was much more than that of max reducible activations. This indicates that the type of the aggregation function really matters. Here, an average aggregation function is potentially a more appropriate candidate for simplification. This is probably because an average function is more representative than a max function when applied to a receptive field. Finally, as we go deeper through layers of a CNN, although chances of convolution reduction increase, convolution reductions using max and average simplification techniques decrease. This suggests that max and average simplification techniques are most beneficial in the very first layers of a CNN. This is because layers very close to the input data inherit higher degrees of the inherent redundancy in the input data. This makes the feature values within very early layers of a CNN more correlated. As a result, max and average aggregation functions can take the most benefit from this correlation. Next, we'll discuss the results of the second experiment. These figures show accuracy and max saving trade-offs for different mask types. Let me explain these figures. First, in this experiment, since we had 2 phases, the training phase and the inference phase, we included 2 types of simplification thresholds, the inference simplification threshold and the training simplification threshold. Second, we experimented with training threshold values of 0.1 and 0.01. The results for each training threshold were averaged over 10 different inference thresholds, which are shown here. The experiments with the inference thresholds very close to 0 resulted in 0, for all the mask types and all the training thresholds. For the remaining inference thresholds, the mask A plot shows the order of measurements as a sample. Okay, now let's discuss two observations. First, from the blue and orange lines, we see that not only the inference threshold, but also the training threshold highly affected the amount of possible MAC reductions. Second, for a 1% top 1 accuracy loss, we achieved almost 11% MAC reduction by selecting mask type A and training and inference thresholds of 0.1 and 0.3 respectively. This amount of MAC reduction may seem non-significant. This is because we were highly short of time, so we reduced the number of epochs to only 2 epochs, and we used just half of our dataset for training our predictors, which it seems to be probably not extensive enough. Also, a multi-class classifier like Reducible usually requires a more extensive training process compared to a binary classifier like ZAP. So, one of the things that we are planning to do next is to conduct a more extensive training. And now to sum up briefly before the QA session. Here we have explained why we are interested in deploying CNNs on energy constrained devices, and also have defined the big challenge to be the high computational complexity of CNNs. To mitigate this challenge, we proposed a predictor called Reducible to identify reducible convolutions, that is, convolutions that can be simplified into much less expensive pooling operations by using a three-step method. The results showed the potential max saving benefits of our proposed approach.